Hi, so this is Unit 10, Solutions and Colloids. So what is a solution? Well, you all are probably very familiar with solutions because you're around them every day. If you are drinking coffee, that's a solution. Tea, that's a solution. Your carbonated soda, these are all solutions. In fact, the very air that we breathe is a solution. So a solution is a homogeneous mixture of two or more substances in which the components are present as atoms, molecules, or ions. The key point is that it's homogeneous and a mixture of two or more substances. What's a homogeneous mixture? Remember, that means that particles are uniformly distributed. If you were to look at a solution, you would not be able to see one part from the other, so uniformly distributed. The particles are too small to reflect light, and so solutions tend to be transparent or clear. That doesn't mean that they don't have color, but you can see through them. They're not cloudy. Particles in a mixture are in constant motion, and they don't settle by the influence of gravity. They will stay mixed forever and ever. And like I said, some solutions can be colored, but they will be clear. You can see through them, transparent, just colored. There's some examples of solvents and solute mixtures or solutions that you may be familiar with. Remember that, here's the definition, a solute is what's being dissolved. The solvent is what's being dissolved into. So our first example, salt water, is where you take some salt, sodium chloride, which is a solid, and you mix it into water, which is a liquid. The solution then is a liquid. And in that case, the solute then is the sodium chloride, the solvent is the water, and the solution is the mixture of the two of them. You can have solutions of different physical states, and then usually the physical state will be, of the solution will be the same as the solvent. So you can see, like I said, solid and liquid is a liquid solution, salt water being an example. Vinegar is an example of a liquid in liquid solution. Carbon dioxide dissolved in water gives us carbonated water, so that's a gas in a liquid. You can actually have solid solutions. They're a little bit harder to see because they're not really transparent, but they are homogeneous in that they're mixed all together. You can't find one part from the other part. So a gold alloy, if you have gold jewelry, generally what it is copper dissolved in the gold to try to give it a little more solid feel, because pure gold is very soft. So that would be a solid and solid solution. Of course, to get them mixed, you'd have to melt them first and then mix them and then let them become a solid again. A dental amalgam, or at least they used to use liquid mercury inside silver, and then hydrogen gas in palladium, which is a solid, is often used as a catalyst, and that's solid. And then some of the other solutions that you may not realize are solutions but are there, is our air. Oxygen is a gas which is dissolved in nitrogen, which is another gas. And actually air is, of course, a mixture of a lot of different gases in nitrogen. Humid gas is when you have water, which is in the liquid state, dissolved in air, nitrogen gas. And then you can also have a solid dissolved in a gas. The ones that we're going to focus on in this class basically are going to be the ones dissolved in liquid. Alright, so this is a little bit of a repeat, but solutions have various characteristics. Again, the distribution is uniform or homogeneous. You can't tell it's a solution. If you look at it, everything is mixed so well that you can't find one part from another. They're almost always transparent. Here's a really important point. You can make solutions of different concentrations, and we'll talk about that later in the next section. Solutions never separate while standing. They always stay mixed, and you cannot filter one part from another. If you took salt water and tried to pour it through a filter, it would all come through. You wouldn't have, you can't separate the salt back out. The only way that you can separate the salt back out would be to use a physical process. So for example, if you heated up your salt water and let the water evaporate, then you would end up with solid leftover. Or distillation, which is the way to separate two different liquids. So when you distill alcohol, you're taking sort of a liquid mixture of alcohol, water, and distilling it to where you get much more pure alcohol. Alright, so what happens if we mix substances? So let's take 3 glasses of water, and let's take a spoonful of sugar and mix it in the first glass. What do we see? Well, the sugar pretty much dissolves, and you have a homogeneous mixture. The sugar dissolves. If you add oil to some water, as you're probably aware, oil and water don't mix, and so basically you'll end up with a layer of oil on top of the water. So that's a non-homogeneous solution. What if we add alcohol to one of the glasses? We'll add 10 drops of alcohol, and the alcohol will dissolve, and so we have, again, a homogeneous solution. So this brings us to a few more definitions. A soluble substance is something that dissolves to a significant extent in a solvent. So in our previous example, sugar and alcohol are both soluble in water. Salt is also soluble in water. An insoluble substance is one that does not dissolve in the solvent. So oil is insoluble in water. Another term that you might hear sometimes is immiscible. That's two liquids that will not mix in each other. Or if two liquids do mix in each other, then you might say miscible. So if something is miscible, it's also soluble. Alright, so what if we keep adding more of each of the substance? So let's keep adding many drops of oil. Well, they're never going to mix. And so we'll end up with a layer of oil that's thicker on top of the layer of the water. So it's never going to be homogeneous, non-homogeneous. What if we keep adding alcohol? Well, it doesn't matter how much alcohol we add. Just keep adding it. It will add at every ratio, and we'll end up with a homogeneous solution. But now sugar is limited, as you're probably aware. So let's add 1 gram of sugar, homogeneous. But what if we add 300 grams of sugar? If we just keep adding sugar, adding sugar, adding sugar. Eventually it's going to stop dissolving, and you'll end up with some sugar down at the bottom. So you'll end up with a homogeneous, non-homogeneous solution. So some solvents you can have mixtures that can dissolve any amount of solute, or sometimes you can have a solute where it's limited. It stops dissolving at a certain point. The solubility then is a measure of how much solute can be dissolved in a specific amount of solvent. So if I say something is soluble in water, generally what I mean is that you can dissolve between 1 and 10 grams of the solute in 100 grams of water. If it's less than 0.1 gram, we call it insoluble. If it's between 0.1 and 1, it's slightly soluble. And if it's greater than 10, it's very soluble. So solubility can depend a lot on the compound that you're trying to dissolve. Here's just some examples of things, solubilities in water. So ammonium chloride, as you can see, is almost 30 grams will dissolve in 100 grams of water, whereas calcium carbonate, which is chalk, only 0.0012 grams will dissolve in 100 grams of water, so it's very insoluble. Gypsum, calcium sulfate, is also very insoluble. Baking soda is somewhat soluble. Sodium chloride is very soluble, almost 36 grams, can be dissolved in 100 grams of water. Ascorbic acid. Okay, alcohol, ethyl alcohol, you see that it's the infinity sign. Ethyl alcohol will dissolve in water to any extent. You could have a cup of water with a drop of alcohol, or you could have a cup of alcohol with a drop of water, and they will mix in each other no matter what amounts. Same thing with ethylene glycol, which is an antifreeze. They are infinitely soluble in each other. Sucrose, table sugar, has a solubility of about 179 grams in 100 grams of water. That just gives you some examples. Some things are more soluble than others. So we can use terms to suggest this also, degrees of saturation. So if we go back and let's say we take that 100 milliliters, which remember density of water is 1, so 100 milliliters is the same as 100 grams. If we put 30 grams of NaCl, since we saw just a minute ago 36 is the solubility of salt in water, so if we put 30 grams in 100 grams of water or 100 mils of water, it will totally dissolve. We'll have a homogeneous solution. It will be completely mixed, but we will have what's called an unsaturated solution because it hasn't reached its limit yet. I could still dissolve more salt in that water. If I took 40 grams of NaCl and mixed it in the same 100 milliliters of water, this would be considered a saturated solution. So what would happen, 36 grams of it would dissolve, and the additional 4 grams would remain undissolved on the bottom of the glass. So that would be a saturated solution because it has dissolved all the salt that can possibly dissolve. So it's saturated. You can also have a solution that is supersaturated. It's not really a solution because it's unstable. I mean, it is a solution, but it's unstable. It won't last forever. And by the name implies it contains an amount of solute greater than what the solubility is under the certain conditions of temperature and pressure. Generally, the way that you can make a supersaturated solution is to heat it up, and we'll talk about this a little bit later also, but when you heat up a solution, you can dissolve more of it in there. So you dissolve a lot, and then you cool it back down, and it doesn't come back out of solution quite as quickly as you might expect, and so it's sort of the solution is a little bit thick, and if you're very careful with it, it won't precipitate out. But it is unstable, so if you jiggle it, or you hit it on the table, or if you add a seed crystal, it'll start the precipitation process, and then once all of the solid has precipitated out, then you end up with a saturated solution once again. This little video, there's a video here where you can see the supersaturated solution precipitating out by using a seed crystal, so you might want to check that out. So what is it that determines solubility? Why do some things dissolve and other things don't dissolve? The most important factor is like. That's what you want to remember. What does that mean? Well, things that have a similar type of attraction to each other will dissolve in something that also has a similar type of attraction. In other words, if you have a polar solute or an ionic solute, they will dissolve in a polar solvent. If we have a nonpolar solute, it will dissolve in a nonpolar solvent. However, generally polar or ionic substances do not dissolve, at least not to a great extent, in nonpolar substances. So if we look at all of our examples, salt dissolves in water because salt is ionic and water is polar. Sugar dissolves in water because sugar is polar and water is polar. Alcohol also dissolves in water because alcohol is polar and water is polar. However, oil, which is nonpolar, will not dissolve in water, which is polar. So like likes like. If you don't remember those attractions, you might want to go back and look, I believe it's chapter or unit 6, where we talked about polar versus nonpolar. Again, we looked at this again back in, I think, unit 5, the solution process. Solution process, what happens is, so if we have a polar solvent like water and we have the sodium chloride crystal, then what happens is the positive end of water will surround the negative ions, the chloride ions, whereas the negative end of water will surround the positive ion of sodium. And so they pull it away, the positive ions will pull away the chloride ion into the solution, and then the negative ends will be attracted to the positive, and they'll pull it away. This YouTube video that I have linked here is a really good one for you to see how sodium chloride dissolves in water. It'd be a really good one to watch. So anyway, the reason the positive end of water attracted to the negative end of the ion, and so there are similar attractions, positive and negative. Sugar also dissolves in water, and sugar has a polar end and a non-polar end. Actually, sugar has some parts of it are polar, some parts, it's all polar. Some parts are positive, some parts are negative. And so again, the positive parts will be attracted to the negative ends of water, and the negative parts of the sugar will be attracted to the positive parts of water. And so because they have similar attractions, positive and negative, they will mix pretty well with each other. This little link that I have on this slide, you may want to look at it. It's kind of a fun, there's actually at that webpage, phet.colorado.edu, you can look at all kinds of chemistry simulations that are kind of fun to shake sugar and water and see what's happening. And so if you want to look into that, that might be a fun thing for you to do. All right, so we showed how polar and ionic mix, and polar and polar. Well, here, nonpolar and polar have different kinds of attractions to each other. So if you can see on the left-hand side, that red molecule right on the border is being attracted much more to the other red ones because there's a polar attraction between them. Whereas the blue molecules in the upper layer are not pulling as hard on the red atom or molecule, and so overall the red ones will pull the layer toward itself, and so these two solutions will never mix because their attractions are so different from each other. There's some other things that determine solubility. Temperature is a really important. We talked about this just a minute ago, where I mentioned that you could heat something up to dissolve more. So temperature can affect the solubility of a solute, but we have to be careful because it will depend on the phase of the solute. So if the solute is a liquid or a solid, then increasing the temperature will generally increase solubility. So as you know, it's easier to get sugar to dissolve in hot water when making tea. Even if you want iced tea, usually what you do is you boil the tea, add the sugar, and then let it cool down. And also to make a supersaturated solution, we do that. Generally speaking, if you heat it up, molecules are moving faster, and so they will mix quicker or easier. Now gases are the opposite. If you increase the temperature, then generally gases will be less soluble. So usually your warm soda is less fizzy than your cold soda because as it warms up, the CO2 evaporates out of it, and so it's less fizzy. And one of the worries about climate change, and especially warming oceans, is that if you decrease the amount, it will decrease the amount of oxygen that can be dissolved in the oceans or in any body of water, and so it will affect the living plants and animals that are in, actually not plants because they grab CO2, but similar CO2 will actually dissolves by a different mechanism that we'll talk about later, but the oxygen will be less there for the animals that live in the ocean. One other factor that can determine solubility is the pressure. Now, it only affects solubility of gases. It won't affect how solids are dissolved in liquids. But if you increase the pressure, the solubility of the gases will increase. So you can see in the picture, if you put a small pressure, some of the molecules will dissolve, whereas if you increase the pressure, more molecules will dissolve in the liquid. And so, for example, when soda is bottled at the plants, they seal it under high pressure, so there's a lot amount of CO2 dissolved, and then when you open the bottle, it will decrease the solubility, and so the bubbles escape. Another example of this is if you are a scuba diver, the deeper you go into the ocean, the higher the pressure your body is under, because you're under all this water. And so the gases in your body will dissolve in your blood the deeper you go. And so if a diver comes up too quickly, what happens is that the pressure decreases rapidly. The gases can't stay dissolved anymore, so they'll escape from the blood. However, you've got veins in the way, and so it will cause some pain when the gases come out of your blood too quickly. And so this is called bends. One other example that I didn't put down here, but if you've ever are treated in a hyperbaric chamber, like if you've got CO poisoning or carbon monoxide poisoning or a burn victims are often put into a hyperbaric chamber, because what they can do, if you're under higher pressure, that means that more of the oxygen will dissolve through your skin to help heal the burn, or to replace the carbon monoxide in your lungs, or anything like that. So that's another. And this law is called Henry's law. If you increase the pressure, you increase the solubility of a gas. This little video here is actually a pretty good one, where you can actually see what happens when you increase the pressure. All right, and one other thing on this little segment of the Unit 10 is, how can you increase the rate of dissolving something? And you're probably aware of this too. So if you're making a solution and you're trying to increase the rate of dissolving, of course, like we just mentioned, if you heat the solvent, molecules move faster, have more frequent collisions, and so they will mix faster. So heating something will make the rate of dissolving faster. Some other things you can do, if you've got a big piece, you can crush it or grind it, so smaller particles have more surface area for solvent to get into and around. So crushing it or grinding it can help increase the rate of dissolving. Or also just stirring it or agitating it, shaking it, or something like that will help increase the rate of dissolving. So anyway, if you want to know some of the picture credits, they're right here. And I will do the second section, or the second section of Unit 10. I'll do another slide presentation.